here. All right, here we go. Close that. Oops.
Land, animal, or land, air, and water.
I know, now I'm just gonna have to go for an interesting animal. Yeah, listen. Well, okay, there is one, but I have that for the final exam. So, yeah, I'm gonna have to run it by Jen, but hopefully it's on an app. It doesn't change the question, it just changes the blurb. Haha. Let's do a tiny bit of review because it was a long time ago. We started two sample means. And sometimes I like to emphasize that these are two independent sample means, right? Because these are two independent groups. The conditions that we check are the same as for one sample t-tests, right? We're still calculating a t, and so the conditions stay the same, but now they are extended to both groups. And so observations, or sorry, independence is the first category. Each group, or each, not each, observations within and between groups are independent. And the normality condition, if n is less than 30, we definitely need to check for outliers. Check for outliers. If n is greater than or equal to 30, you may as well check for outliers, but you can relax it a little bit. Okay. The outlier condition is relaxed. So we can handle some non-normality as long as our sample size is big enough. The outlier condition can be relaxed. And then in terms of what we do, it's all on your formula sheet. I know. I would probably hate it if I was in a class and my teacher kept telling me that, but it is. It's all on the formula sheet, okay? And so here, two sample means tells you the type of question, but also emphasizes, so just as a little nudge in the right direction in terms of your conclusions, it's about the difference of two means, right? So mean one minus mean two. Just as before when we had two groups, doesn't matter which is group one or group two, as long as you establish them and you're consistent, then you're safe. Okay? You can build a confidence interval or do a hypothesis test, right? And we had kind of, or we could do H naught is that mu1 minus mu2 equals 0. And HA mu1 minus mu2 is not equal to 0, but of course this sign can change. The reason I don't tend to use this one as much is, although it matches what my hypothesis is about, right, and what the question is about, how mu1 minus mu2 compares to 0, it can be a little bit tricky to figure out the sign here, like we saw with paired data. So that's why if I just use this one, right, all I've done is moved mu2 over to the right-hand side, and you could rejig it that way, but whichever one you want to use is totally fine by me. I will know what you mean. Okay. It's down here in the corner, but if we're using the table, so if we're doing calculations by hand, our degrees of freedom is going to be your smaller sample size minus 1. So n1 minus 1 or n2 minus 1, you take the minimum of those two, which is the same as the smaller sample size minus 1. And if you're using software, right, to run the entire t-test, then it'll use a different degrees of freedom, but that's okay. It's going to be close anyways. And then our t is calculated the same way. How far is our observed difference from the hypothesized difference of 0, taking into account the spread, which in this case is slightly larger because we have standard deviations and sample sizes from both groups. Okay. From last day, we finished, we checked the conditions. Okay. I'm going to bring this in again so that we have all the information. But we checked the conditions. So this was when an instructor decided to run 2 slight variations of the same exam prior to passing out the exams. She shuffled the exams together to ensure each student received a random version. Summary statistics of how students performed on these 2 exams is shown here. Anticipating complaints from students who took version B, she'd like to evaluate whether the difference observed in the groups is so large that it provides convincing evidence that version B was more difficult on average than version A. Okay. Continuing from last day. All right, so here's the question again that we just read. And we've got sample sizes for version A and version B. And so as soon as I see 2 different sample sizes, that's a clue that this is 2 independent sample means, right? Because if they're paired, they have to be the same sample sizes, right? Because you have to have that number of pairs. So in this case, it's obvious that it's a 2 sample means question. And you can confirm that by making sure that you have 2 sample means and 2 sample standard deviations as well. Right? I'm not going to copy it, but we'll review it. Okay, so we checked the conditions. We said that, okay, well, since students were randomly assigned a test version, so then the groups are independent of each other, right? They're randomly assigned to the groups. So that's between the groups, it's independence, but we also assume that students are independent of each other. So then they're independent within as well. Okay. This was one of those where we assume that that's the case, right? And that's not necessarily true, but we have to assume that it is, right? That students are independent of each other. The normality condition, we check the sample sizes. Both of them are, so 27 is less than 30, so we would definitely need to check it for outliers. 30 is 30, that's a fact. So we may as well check it as well, right? Because it's kind of borderline. So given the minimum and the maximum values, right, we can use those values to figure out, okay, if I standardize all these, which we did, then we find that all these values are within 3 standard deviations. So we can assume that there are no outliers. So we already checked the conditions, and the conditions for inference are satisfied. From last day, we concluded the conditions for inference are satisfied. Okay, now we're ready. And this question is asking for a hypothesis test, right? And so here provides convincing evidence what this means is do a hypothesis test. Okay? Whenever you want evidence, right, then, and it doesn't ask for a confidence interval, we will do a confidence interval just for practice. But here, what it's asking for is a hypothesis test. Little sneaky. Yeah. Okay, so let's say step 1 is state the hypotheses. The null hypothesis is going to be that mu A equals mu B, or if you prefer, mu A minus mu B is equal to 0. I encourage you to use question-specific subscripts, especially if they're nice and clean like this, A and B, right? And so then you'll be able to, it doesn't matter in the null hypothesis, but of course in the alternative hypothesis, then it's going to make a difference. All right, here's where we need to put our thinking caps on and say, okay, version B, so we want to know if there's convincing evidence that version B was more difficult than version A. Okay. Now, if it's more difficult, the grade would be lower, right? And so here we look at 74.1 is less than 79.4. We just want to know if it's significantly less than 79.4. Okay. And so here, in terms of the population grades, we're going to say either mu A is greater than mu B, right? If version B is more difficult, right, then that would be the case. Or if you prefer in terms of the difference, mu A minus mu B is, I have to usually, mu A minus mu B, I subtract mu B over here and then is greater than 0. That's the part that I find is a little bit more difficult for me to wrap my head around. So that's why I prefer this one. They're the same. There's no, I hate to say difference. It's all about the difference in mean and if they're different from 0. Yikes. This doesn't look like a beat. Okay. And so either way, doesn't matter. Right. These are null and alternative hypotheses. You only have to do one of these, obviously. And you just want to make sure, so greater than 0, okay, if the mean of A is higher than the mean of B, right, then take an example, 2 minus 1 is 1, which is positive, right? And so it's greater than 0. So it checks out. So this one you do have to be a little bit more careful about. Because I only care about one extreme, this is a one-sided test, right? And I like to make a note of that here, right? A one-sided test. We don't use that until we need to find the p-value, right? But that's when you need to know, okay, is it a one-sided p-value or a two-sided p-value? And so if you've already made a note of that here, then you can quickly refer to that and I can go down there to the p-value. That's something that a lot of students struggle with usually. How do I know if it's a one-sided p-value or two-sided p-value? And it's because of the disconnect that it's way back in the alternative hypothesis. So step 2, do the test or calculate the test statistic if you're boring. Maybe not boring, if you're proper. T, I don't know where I am here, so that's okay. The formula for T, everyone has it memorized. No, they don't. I do. x1 bar minus x2 bar over the square root of s1 squared over n1 plus s2 squared over n2. This little square here trips people up often, right? You forget to do that little square, and so that's going to be important. So in our case, let me grab just this information here. There. All right, so we've got A and B. I'm just gonna let one be A and two be B, kind of lazy. That's okay. As long as you're consistent, right? It doesn't actually matter. And even consistency doesn't truly matter. But you don't want to swap your N's and your S's, right? As long as they go together, then it's okay. But let's not be too sloppy. All right, x1 bar is 79.4 minus x2 bar, which is 74.1. Remember, we're technically seeing how far that is from a difference of 0, right? And then we need the standard error of this thing, which is going to be quite large. S1 is 14 squared divided by N1, which is 30, plus S2, which is 20 squared divided by N2, which is 27. Because technically it's your point estimate minus the hypothesized value. And the whole point estimate is x1 bar minus x2 bar. But really what you're checking against is the difference between mu1 and mu2. But we always assume the null hypothesis is true. So regardless of if mu1 is equal to mu b, or mu a is equal to mu b, mix them all up, then the difference between those is 0, or more explicitly, mu a minus mu b is equal to 0. And so this is 0. Right. And that's always going to be 0. So that's why it's not even on the formula sheet. Right. But it's the important part there is that we always do hypothesis testing, assuming the null hypothesis is true. Right? We assume that these two means are the same until we have proof otherwise. And then just for completeness sake, the standard error of the point estimate. So, okay, great. I can't remember. You guys can, yeah, okay. It was when I was splitting the screen, you guys couldn't see it. So I'm just gonna use this calculator here because there's a lot of calculations. And where do I have my numbers? 79.4 minus 74.1 is 5.3. So really what we're seeing is how far is 5.3 from 0, right? Taking into account the spread. So we want that guy divided by the square root of, and I'm gonna use and abuse my brackets here. Let's see here. How did I do it? Okay. S1 was 14 squared, and then divided by sample size of 30. Oops. Delete 30. Close that bracket, but stay under the square root. So be super careful. And then 20 squared divided by 27. Oops, wrong place for a bracket. I get 1.147. I'm going to screenshot this. I'll bring it in. Crop it up. Okay. So T is 1.147 to 3 decimal places. 3 decimal places because then it matches the table, right? Okay. So now, right, what would the change if you swapped A and B and used B as group 1 and A as group 2? That feels weird, right? But the only change would be that this is negative, right? And I can't remember exactly, but I think I went through and changed all the assignment questions so it takes either or, unless it tells you to use one or the other, but it should accept either or. Right. Okay, so step 3, now we're ready to find the p-value. In order to find the p-value by hand, we need, well, in any scenario, we need the degrees of freedom. And so the degrees of freedom is the minimum of n1 minus 1 and n2 minus 1. And for these, because it would take a ton of space, I do write across the page again for a lot of my degrees of freedom calculations. Sample size 1 was 30 minus 1 or 27 minus 1, which is the minimum. And I'll bump this down here. Minimum of 29 or 26, the minimum of those is 26. It's technically what you're doing, but if you want to just take the smaller sample size, which is 27 minus 1, you get 26. Right, so it doesn't matter how you got there. Okay. Now we're ready to use the t-table with 26 degrees of freedom. Let's see here. I'll just bring in this whole thing, kit and caboodle. Remember, if you don't have your degrees of freedom that you need, right, you always need to bump it down. So decrease the degrees of freedom. So if you're choosing between 30 and 40, right, you would go down to 30. Even if you have 38 degrees of freedom, right, you're closer to 40, but you have to bump it down to 30. In this case, 26 is on here, so we use that. Okay. So now we take our t, 1.147, we take the absolute value of that. And how I like to set it up is I put it in the middle of the page as my calculated t, and then I have my less thans on either side of that. And so my general setup is something like this. So since the absolute value of t equal to 1.147, I think it is, yep, is between some two values. So here 1.147 is between these two values. So I'm going to jot those down, 1.058 and 1.315. This is a good opportunity to check and make sure that what you're saying makes sense, right? Is 1.147 between the two values that you just told me? Sometimes it's not. Then that's a way to check it. Okay. So then, now we need to decide if we need a one-sided or a two-sided p-value. And because we only care about one extreme, right, our one-sided p-value is between 0.1 and 0.15. And of course, there's a real value associated with a T of 1.147, but you would use software. So this is good enough. We can use this to draw our conclusion. So step 4 is your conclusion. Your conclusion still has 3 parts. Right? Compare the p-value to the alpha level. Then what is your conclusion in terms of H naught? And then what's the conclusion in terms of the question? Right? And so here, since the one-sided p-value is between 0.10 and 0.15, we were not given an alpha level. That's okay. The default is 0.05, right? And so it is not less than the assumed alpha level of 0.05, which means we do not have enough evidence to reject H naught. We do not have enough evidence. Notice things where I'm showing off. I want you to show off too, right? You know what type of p-value you have, right? You know what the values are. So it's just really sloppy when you don't support your conclusion with the values that you found earlier, right? And so here, support your statements with the values found earlier, right? That's why you did it. Okay, we do not have enough evidence to reject H naught. If you are the teacher, you're kind of happy about that, right? Why? It means that there's no significant difference in the average grade for each of the versions, right? And so that's going to translate to difficulty, right? Unless, you know, the groups weren't random, but we were assuming that they are, right? And so, therefore, there is not convincing evidence to say version B was more difficult than version A. I think that was like the, I don't know why. Like the question. Let's see here. Provides convincing evidence that version B was more difficult on average than version A. So that's what we want to say. There's not convincing evidence to say version B was more difficult on average than version A. Okay. What if we want to construct so just a follow-up question? How large were the differences in grades on average? How large is the difference in mean grades? In order to put a value to how large the difference is, we're going to construct a confidence interval. And let's do a little bit of brain work here. If we used an alpha level of 0.05, there, need my pointer, 0.05 for a one-sided test, right? So here, that's going to look like this. Difference greater than 0, put 0.05 in the upper tail is what we were allowed. So now for a confidence interval to match that conclusion, I'm going to put 0.05 down here in the lower tail as well, which means that I have a 90% confidence interval in the center. So construct a 90% confidence interval for the difference in mean grades. So the confidence interval is x1 bar minus x2 bar plus minus t star times that same standard error, s1 squared over n1 plus s2 squared over n2. The only thing that we don't have already is the t star. So we need t star for a 90% confidence interval with 26 degrees of freedom. We already know the degrees of freedom. And so t star with 26 degrees of freedom is, let's see here. Oh, went to the wrong spot. We'll do this. I'll bring it in. It's hardly worth it anymore because you guys are hopefully really good at using the table by now. But it doesn't hurt. Just takes some time to match it up mostly. There. Okay. So I want a 90% confidence interval and I have 26 degrees of freedom. So t star is 1.706. I'm going to do something sneaky and recycle my calculations here and just ditch the difference if I can. There. So my standard error is 4.62, blah, 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 blah. And then now, what was my t star? 1.706. So let's do this. Can I? Nope. I'm gonna call it M equals, so the margin of error is 1.706, oops, 0.6 times the previous value. That's the t star. Because we already calculated this standard error before. So what I encourage you to do is, I don't think I'm going to make you do a follow-up confidence interval, but if you had to, then you would just recycle that standard error and not recalculate it because it's kind of a big calculation. All right, so you're allowed to do that if you've already calculated it, which we have. So now the difference is 5.3. So 5.3 minus M is negative 2.58, and then same thing, 5.3 plus m is 13.18. Oops. I'm going to bring this in. So then the confidence interval is negative 2.582 up to 13.182. This matches our conclusion, our previous conclusion, right? Because a difference of 0 is in the interval, right? This is an interval for mu1 minus mu2. And so a difference between -2 and +13, a difference of 0 is entirely possible. And so we're 90% confident of it. And so that's why there's no significant difference in the grades. So now we can interpret this, but as long as you remember that you're talking about the mean difference, right? Sorry, the difference in the means, as I emphasize something, I stay wrong. The difference in the means, right, as opposed to the mean differences for paired data, then you're okay. So we are 90% confident the interval from negative 2.58, let's go to, sure, 3, to 13.182 captures, right, that's a keyword, captures the true difference in mean grades. The true difference in mean grades between version A and version B, I should say. Between version A and version B. You can translate that to, okay, well, if you're doing version A minus version B, right, a difference of negative 2.58 is saying that version A had a higher grade of 2.58, right? Or version A had a higher grade of 13.18, right? So you can make that extension, but I want you to just stick to rephrasing the question as an answer. Okay. There, 2 sample means. Done. I will say 7.4, which is on power calculations. For a difference of 2 means. I'll let you read that on your own, but I promise it's not tested. Okay, so you can read it if you want to, if you're interested, but it doesn't really serve us, and so I skip it. Read on your own, which really means it's not tested. There, 7.4, done. 7.5. Oh, you think so, huh? I know, right? Yeah, just rattling off sections, nobody's business. Here comes another one. So 7.5 is the last section in chapter 7, and which means it's the last official hypothesis testing type of question that we're going to do, unless we get to some regression hypothesis testing. But that's fun. It's not as rigorous as this stuff. Comparing many means with ANOVA. Now let's just clarify. ANOVA stands for analysis of variance. Which used to confuse me a lot, because even though it's called analysis of variance, now I understand it's using it in the background, but kind of on the front end, what we're actually doing is we're extending it. So we're not just comparing two means to each other, right? Or one mean to a value. Now we're comparing many means, right? More than two means. And so even though it's called analysis of variance, we're actually analyzing if there's a difference in the means. So analyzing more than two means or groups. Right? Version A of the test, version B of the test. What if there's a version C and a version D of the test? Right? Then what do we do? So that's where the ANOVA comes in. And so one of the main cautions here is, although it would be tempting, so let's just talk about three versions of the test, A, B, and C, right? So it would be tempting to say, well, I can just look at how does A compare with B, and how does A compare with C, and how does B compare with C, and do those two sample t-tests again. I can do that, okay? The problem is that I'm opening myself up to a type 1 error every time I do that, right? So that's a problem, because now I've opened myself up to not one alpha level of 0.05, but three of them, right? So the probability of making a type 1 error is a lot higher now. So the ANOVA is what we do before we do those pairwise comparisons. We will do those pairwise comparisons, but what the ANOVA does is, I think of it as, for some reason, all my data are kind of inside a box, and I'm looking down into the box, and the ANOVA just goes, hey, is anyone different in there? And then if you get a significant ANOVA, then yes, there is something in there that's different. It doesn't tell us what is different, it just tells us that yes, there is something in here. There's one or more groups in here that are significantly different from each other. Okay? And so, yeah, I kind of think of it as, hello, anything going on in there? And then the ANOVA says yes or no. If the ANOVA says no, we're done, right? That there's no reason to probe further, right? And so it's kind of a nice kind of thing to do before you go and spend all your time doing pairwise comparisons, especially if you think back to before calculators and stuff like that. If you didn't have to go through and do all those calculations, that would be nice, right? Okay, so let's summarize that. So let's say we want to compare the means of three groups. We want to compare the means of three groups, right? A, B, and C. I'll do it in red. It might be tempting to do individual pairwise comparisons. It might be tempting to conduct individual pairwise comparisons. Right, so for example, A with B, oops, A with B, there's no difference. A with C, and B with C, right? Each one of those would be a 2-sample t-test. 3 2-sample t-tests. You can do that, and we will do that, but we have to make adjustments. So we'll get there. Okay? But the problem is that each pairwise comparison, like I said, introduces the same probability of making a type 1 error. Each pairwise comparison introduces the same probability of making a type 1 error. What's a type 1 error? Rejecting H0 when I shouldn't have. Rejecting H0 when it should not be rejected. Which, if we apply it to these comparisons, right, if I reject H0 and I say that A is significantly different from B, for example, right, but I'm wrong, that could be really bad, right? And so for each one, right, I'm increasing the probability of making a type 1 error. Tests. Do you mean here? We usually, so when you do calculate a t-test statistic, you just call it a t-test. And it's kind of the broad term. It can mean 1-sample t-test or 2-sample t-tests. And we just finished 2-sample t-tests. Okay. So we will have methods to work around it. Okay. So here we will introduce ways to work around it, or to work around this. Let's leave it at that. But first, we would conduct an ANOVA. Just a period. So the ANOVA, or an ANOVA, so the analysis of variance, an ANOVA, like I said, does not tell us which group is significantly different from one or more of the other groups, right? But it does tell us if there is something significant in there. Right? Let's do this one in pink here. I usually say ANOVAs, analysis of variances, sort of, I guess. ANOVA became its own word at some point. I don't know. You run ANOVAs, analysis of variance tests. How about, I'll try to be proper. ANOVA tests, ANOVAs. There. That doesn't make grammatical sense, but it makes sense to me. ANOVA's possessive. do not tell us which means, potentially more than one, are significantly different from the others. But it does tell us that there's at least one mean that's different from the others, or if there is at least one mean. But it does tell us if there is at least one mean that is significantly different from at least one of the others. That is significantly different from at least one of the others. Okay. So there's a chunk from the textbook that I'm gonna grab here. Gotta scroll there though. There's all that fun stuff you can read on your own, power calculations. All right. So this one here feels like a lot to write down. So 7.51, core ideas of ANOVA. So in this section, we'll learn a new method called analysis of variance and a new test statistic called F. Okay, so we're going to calculate an F test statistic. Okay, so it's a new distribution similar to the chi-squared. It's also skewed, and we'll kind of see what it looks like. But the F statistic is associated with ANOVA. Now, what gets complicated later on is we can run an ANOVA, just like we use a t-test, we can use a t-test for one sample means, we can use a t-test for paired data, we can use a t-test for two sample means. Same way we can use an ANOVA for means, we can use ANOVAs for the betas in regression, right? So for the coefficients in regression. So there's a lot of uses for an ANOVA. So it's kind of a jack of all trades. Okay, but the ANOVA follows an F distribution. And so ANOVA uses a single hypothesis test to check whether the means across many groups are equal. So same as before, our null hypothesis, usually we end up writing it in words. I like to just use the notation again. So instead of mu1 is equal to mu2, now I have mu1 is equal to mu2 is equal to mu3 is equal to mu4 all the way up to mu k, which means that we have a subscript k. K is the number of groups. So when we were comparing A, B, and C, right, we had 3 groups, and so K would be 3, right? And so the list would end at mu1 equals mu2 equals mu3, right? And so in words, right, the mean outcome is the same across all groups, which means there's no significant difference here. Everyone's basically the same, right? No significant difference. The alternative hypothesis is that at least one mean is different. Yeah. So another way that we could write this is the alternative is that mu I does not equal mu j for at least one I not equal to j. But if you want to use words, that's totally fine, right? At least one mean is different, that's safe. But if you prefer to stick with the notation, then that's what it would be. Okay. For our conditions, right, we're going to check 3 conditions. So it's an extension of the conditions for the t-test. And so the observations are independent within and across the groups. That's the same as a 2-sample t-test. The data within each group are nearly normal. So that's if the sample size is less than 30, then you have to check for outliers, right? And so these 2 first conditions are the same as 2-sample t-tests. Oops. And then this one is new, right? New for ANOVA. The variability across the groups is about equal. Okay. So this one we'll come back to because that's a new one, right? And so we'll parking lot this, but I will talk about it and how do we check it. So when these 3 conditions are met, we may perform an ANOVA to determine whether the data provides strong evidence against the null hypothesis that all the mu I are equal. Okay. What's really nice is that these are always going to be your H0 and HA for ANOVAs, right? As soon as you've identified, okay, I'm comparing more than 2 groups, okay, I'm probably going to have to do an ANOVA. Then these are these will always be H0 and HA for ANOVA. I'll say for us, because I don't anticipate talking about ANOVAs for regression. So for us, this is the only one that you need. Okay. So let's talk about this new condition. Copy. Okay. To check this condition, usually what you would do is, okay, so we want to have the variability. The variability is the spread, right? And a measure of spread is the standard deviation or the variance. Okay, so the spread, which is things like the standard deviation or the variance, talking about, so comparing the number values of the standard deviations might be difficult, right? If they're relatively the same, then you're okay. But what we do usually is we just visualize this with side-by-side box plots, right? Because if the box plots are relatively similar in width, then you can assume that the variability across the groups is approximately equal. To check this condition, to check the constant variability condition, we usually consider side-by-side box plots. If the width is similar across the group, so if the width of each box plot is similar across the groups, we can assume the condition is satisfied. And I'm gonna grab an example here. Okay. I think this is from a baseball example, but let's just page 287. Oops. Hey. Yeah, just an empty box. I'm gonna bring this in because I think that we want to. We'll do this whole example. But so for example, we've got these outliers here, okay, and some down here, but in general, so you're just kind of blurring your vision, and in general, right, kind of looks like this, like this, like this. They're roughly the same, right? A concern would be if you had something like this, right? And so here, the widths are roughly the same. So we may assume the variability across groups is equal. The variability across these three groups is about equal, using the same wording as that bullet. Okay. So that's the only new thing that we need to check. And usually we can kind of, we're pretty flexible on this condition, right? And so it's just, if there's something glaring, then that's a problem. Notice that I'm ignoring the outliers because there's only one or two values. So get a little cheeky there. All right. Let's talk about the F statistic. The F statistic is interesting because it has two sets of degrees of freedom. So the analysis of variance ANOVA is used to test whether the mean outcome differs across two or more groups. ANOVA uses the test statistic F, which represents a standardized ratio of variability in the sample means relative to the variability within the groups. So in behind the scenes, it is analyzing the variance between the groups. But if H0 is true and the model conditions are satisfied, the statistic F follows an F distribution with parameters. So the first degrees of freedom is going to be K minus 1, which is the number of groups minus 1. Remember? So K is the number of groups. And the second degrees of freedom is N minus K. So your total sample size minus K. So minus the number of groups. And maybe I'll say total sample size. Just like the chi-squared, the upper tail of the F distribution is used to represent the p-value. And so just like the chi-squared as well, it's going to change the shape So depending on what degrees of freedom you have, that's going to determine the shape of the distribution. But in general, it's going to be skewed to the right. And so only the right tail is the p-value. Okay. So actually, go back there. Usually what we have is we have a table of output like this. So I'm not going to get you to do the hard work of generating this table, but you do need to know the anatomy of this table. Okay, so that's where we're going to focus. Okay, and so here we will not generate this table from scratch. Because there's quite a bit of work that goes into it, and we have software now, so we don't need to. But you do need to know the anatomy of this table and how each cell corresponds to the other cells. Okay? But you do need to know the anatomy of this table and I'll say the relationships between the cells. Yeah. Okay. So ANOVA output is going to look like this. So it has 2 degrees of freedom, and here this is going to be your D, or maybe I'll, you know what, I'll blow it up. But position here is going to be the general group name. And then there will always be residuals. So it's going to be the group and the residuals. Okay. So if I grab this, okay. So in general, how can I make my, let's call, oh, need to draw it back. You're gonna have a group name and residuals. So just in general. Okay. There are some degrees of freedom. And so this is what we said. This is your degrees of freedom 1, which is your K minus 1, which is your number of groups minus 1. So DF1 is equal to, I'll put it down here. DF1 is K minus 1. And DF2 is N minus K. Sometimes there's a total row down here, but we don't have that right now. Okay, so then what happens is I'll give you the sums of squares, okay? But often I'll also give you the total, which is DF1 plus DF2. This sums of squares we usually call SS, and we can call it SSG and SSR for residuals. So then the total sums of squares is going to be SSG plus SSR. You just add them all up. Okay. Given two of these three, you can find the third, right? Knowing that they have to add to the total, right? So usually that's how I kind of jump start you, is I'll give you the total and one of the other two, and then you have to remember that, okay, well, they have to add to the total, so then you can find the third one. Okay? So this is where a lot of the work goes into if you're doing it by hand, so that's why I kind of give you what you need. And then once you have the sums of squareds and the degrees of freedom, then the mean squared, so here the mean squared, the relationship between the mean squared is that it's going to be the sums of squares divided by its degrees of freedom. Okay? And so here, let's see MSG and MSR. So MSG is the sums of squared for the group divided by DF1. Oh. And the mean squareds for the residual is the sums of squared for the residual divided by its degrees of freedom, DF2. So if you have the sums of squareds and you have the degrees of freedom, then you can calculate the mean squared, right? You just take the sums of squared divided by its degrees of freedom, sums of squared divided by its degrees of freedom. So now, okay, we don't care about what these values, we would if we had more time to spend on this, but usually that's more of a second course type of deal. Okay, and so for us, right, we know that we need an F statistic, right? So what we're here for is this F value. Now this F value, or just F is the previous column, MSG divided by MSR. So you can see how you can kind of like daisy chain through here, right? And all the values are all linked. And then this p-value is from an F with DF1, DF2 degrees of freedom, and it's the area in the upper tail is the p-value. We've seen that before with the chi-squared, right? Where it's not symmetric anymore. So as soon as it's skewed, then the p-value is just the area in the upper tail. But then once we have the p-value here, in this case, 0.0066, right? This tells me that, okay, then I have enough evidence to reject H0, which means that there's at least one of the group means that are significantly different from at least one of the others. Okay. So if we go through this problem properly, let's see here. So they show you how to calculate those sums of squareds and the mean squareds by calculations, but I don't want to do that. Here for one thing only. It's a long question. Okay. Especially because I don't really know anything about baseball, but that's okay. We'd like to discern whether there are real differences between the batting performances of baseball players according to their position. So there's the outfielder, the infielder, and the catcher. And you can grab this data set if you wanted to and generate all this output. But there are 429 Major League Baseball players from the 2018 season who had at least 100 at-bats. So that defines our population. And so here, I'll include the top here. Copy. I think I hit copy. Just hit it again. because then it just introduces the data set, which we're just going to use blindly. But if you want to, you can follow along and recreate these things in R. It's not too bad. I think it's the AOV function. Okay, so first, the conditions. We have the independence condition. Now, we were told, so we have, oh, I'm out of time. 1 minute.
Oh.
I know, time flies when you're having fun and doing an ANOVA. We'll pick up there next day. Just as a quick note though, I did post practice for the quiz. There's not a ton of ANOVA practice because I usually don't get this far. And so you might have to go to the textbook and try some of the textbook problems as well, right, if you want more practice. All right, and it's a huge practice for quiz 4, but the solutions are up already, so you're good to go. Let me know if you have any questions. We'll pick this up next day. Stop this recording.